Hi class, we're going to try the video one more time, see how that works for you. Mostly I'm doing it because I want to show off my t-shirt. Look at that. Now everybody has a Spock t-shirt that says live long and prosper on the back. So, now you should feel special that you got to see that. We're going to talk about asteroids and comets today, and they're kind of cool. These are from the leftovers of the solar system. So when the solar system formed and the disk around the sun, we ended up with these 8 planets, but there were leftovers. There were things that ended up not in a planet that condensed out of that same disk. We had rocks, we had comets, we have other things. So we're going to talk about those today. So if you notice right between Mars and Jupiter, there's an arrow. That is where the asteroid belt is. So that's where the rocky debris ended up. And if you look farther out to the other blue arrow past Neptune, that's where more of the icy stuff ended up, the leftovers of the icy stuff are comets. So the asteroid belt. The movies like to depict the asteroid belt as a bunch of rocks being all close together. That's not what it is. And if you watch that first YouTube video of Star Wars and how they're dodging rock after rock after rock, that's not how the asteroid belt really is. There are different types or different sizes of rocks that are floating around, but they're very far apart. Perhaps even as far apart as from the Earth to the Moon. We send spacecraft through the asteroid belt pretty often and haven't hit a rock yet. So the asteroid belt is not that crowded. So there's a video here that you may or may not be able to access by clicking on the link movement in the belt, but it kind of shows you how the rocks move around. Now they had to make these for the animation look really, really big, but they're not, and they're not quite that crowded, but it does show how they travel around. So in the asteroid belt, we actually have planet-looking objects. This is Ceres. It's the largest object in the asteroid belt. And it's kind of special because it's round. Now, what makes a planet round out is its size and its mass. So if it is a bigger object, then the gravity from the center of the object is pulling the sides from all directions and rounds out the body. So this was big enough to round out. So these are the biggest asteroids in the asteroid belt: Ceres, Pallas, Vesta, and Hygiea, and what years that they were discovered and their diameter in kilometers. We sent a spacecraft up in 2007 to go investigate 2 of these asteroids in the asteroid belt. Did a Mars flyby, and then it went to the planet Vesta, or the asteroid Vesta. It was called the Dawn mission, and it orbited Vesta for a little while, and then it went on to visit Ceres, that one that I just showed you a picture of. So this is kind of cool. This shows the pictures that this Dawn mission took of those 2 asteroids as it got closer, closer, closer. So looking at Vesta there, it's really fuzzy at the beginning, and as it gets closer and closer, it gets really quite clear at the end. Now notice Vesta isn't completely rounded out. It is actually a smaller body than Ceres is, even though the pictures here don't show them to scale. It's smaller, so it didn't completely round out. But notice also how cratered they are. Everything in space is moving. Everything's getting hit by something else. So heavily cratered. Ceres. Ceres was kind of fun. When this mission was up there and started getting its first images of Ceres, they saw this white spot. And they could see it from a distance. You can see it from the far away images. And then as it got closer, it got brighter and brighter. And everyone's like, what is that? We couldn't wait to kind of see what that was. And they were able to do an analysis of it by its spectra, and figured out that it was sodium carbonate. Now this is a kind of a residue that we get around hydrothermic vents on Earth. So it could have been spewing from inside at one time, and that was the result of getting these mineral deposits in this white spot. And there's kind of a close-up of this mineral deposit. Kind of cool. So Ceres is about the size of Texas. And if you remember what differentiated means, it means that there is the heavier stuff went to the center and the lighter stuff is on the outer edge. They expect that Ceres was probably like that, where it is differentiated within it. There's a good picture of Vesta. It's a very bright color. They say you can even see this if you know where to look with the naked eye. I personally have never seen it, but I really haven't known where to look as well because it's orbiting all the time. But it's a very bright asteroid because of its surface. And there is a family portrait to scale, so you can get an idea of how big they are. Not very. So there's Earth's moon, and Ceres is quite a bit smaller, and Vesta is smaller than that as well. These are called the Lagrange points, named after a French mathematician who calculated this many hundreds of years ago. And he figured out that there must be spots where the gravity of the sun and the gravity of a planet kind of equal out, and the pull from the outer planets even perhaps are all kind of balanced. And these are called the Lagrange points. So from where L1 is, there's a little tiny green dot there. So the pull from the planet Earth and the pull from the sun at that particular spot is balanced. And then you go to L2, there it's outside of the Earth, and that's another spot where the gravitational pull from outside and inside is kind of balanced. And we have L3 on the opposite side of the sun, L4 and 5 at 60-degree angles. So these are kind of special spots, and they're very useful to us because that's where we like to plant spacecraft. If we want a spacecraft to orbit with the Earth, and we want it to not take a lot of fuel for corrections, then we plant it in one of those spots. And then it can travel with the Earth, it's pretty well balanced, and if it does need a correction, it only takes a little tiny bit of fuel to do that. Now, because these are gravitationally balanced spots, they also do something else. They also trap asteroids. So here's the Lagrange points for Jupiter. There's balance points between it and the sun, and then there's those 60-degree angles again. So asteroids that have come in, been trapped by Jupiter's gravity, and ended up in those Lagrange points, they are still there. And we have a whole bunch of asteroids that are called Trojans that are in those Lagrange points. So this picture kind of shows how that is, and they orbit, some trailing Jupiter and some in front of Jupiter, and then we even have sort of a triangle reddish part that are inside. Those are the Hildes. The green ones are called the Trojans. Now, Jupiter isn't the only planet to have Trojans. Looking at this chart, you can see that Jupiter has 6,000 or more, but Venus has 1, and Earth has 1, Mars has 7, Uranus 2, and Neptune 18. So these are rocks that were flying by, got caught in the gravity, and ended up in those balanced points and just orbit with the planet. This is the position of an asteroid that orbits with Earth, and it's just from the perspective of Earth how it looks like it does sort of a loop-de-loop. Now, some interesting things is some of these asteroids actually have their own moon. So Ida is 56 kilometers in its long dimension. It's a little tiny asteroid in the asteroid belt, but it has a little tiny moon that we call Dactyl, and it's only 1.5 kilometers across, and they travel together. So we have these near-Earth objects. So how scared should we be? Well, they have this graph here showing the sizes that we've been able to map. So there are a lot of sizes. The blue are all of them together. The yellowish color are 140 meters plus. But the red ones are the ones we care about. The red ones are bigger than a kilometer, and if they were to hit Earth, it cause some damage, and it wouldn't be a good scenario. So with expected of lifetimes of about 10 million years, the ultimate fate of the near-Earth asteroids may be gravitational ejection from the solar system or collision with one of the terrestrial planets, in particular NEAs that come especially close to the Earth, which are large enough to threaten civilization, are labeled potentially hazardous asteroids. Do not spell civilization that way. That is really sorry. I'll have to fix that. So we keep track of these asteroids. It's kind of interesting. We have a whole department that tracks these so that we know what's going to come hit us and kill us all, even though we can't do anything about it. We have no defense. We have no spacecraft like in the movies that we can shoot up a nuclear explosion and break it into little pieces and make it not hurt us. We don't have that. But we keep track of them so we can know what's coming, and this is recent. This is April this year of different asteroids that are coming in, and it has the distance that they are in AUs or in lunar distances. So you can kind of look, and then in the last column there it shows how big they think they are, because we can't really get exact on them, but how big they think they are. So if you want to know what's coming, you can look this up on the website. It's just Google near-Earth objects, and you'll be able to find this page. So when we have asteroids hit each other, they break into pieces, and sometimes some of those pieces end up are meteors that come to Earth and land on the ground and become meteorites. And we have different types. They call them C-type, S-type, N-type, rare types, but they all are designated different types because of what their composition is. So let's look at those for a minute. So the C-type. This includes more than 75% of the known asteroids. They're extremely dark. They're similar to carbonaceous chondrite meteorites. Approximately the same composition as the Sun, minus hydrogen, helium, and other volatiles, meaning things that evaporate. There's S-types. These are pretty bright. They're kind of metal and nickel and iron. And then we have M-types that are most of the rest. Pure nickel, iron, metals. And then there are the other types. There are lots and lots of subdivisions of different types of meteorites. You can actually spend your whole life studying meteorites. So this shows the distance between them, or between the Sun and where they are located. So that's the asteroid belt from 1 AU to 5 AUs on the bottom of the graph. And so the stony type that are closer in, we have the C-type that are farther out, and then we have the M-types that are metal, kind of in the middle there. So why do we have different compositions? So let's remember what the word differentiation means. My favorite word, differentiation, which you will see on tests because I like the word so much. I am going to stop this video right now and keep you in suspense because I'm out of time for this one. So think on differentiation. What is it?